Here, the G-man effect I will describe in this class, and the G-man effect. And when we study in the modern physics, and we study the G-man effect. G-man effect is when you apply magnetic field, the energy level splitting of the hydrogen, and we call it is G-man effect. That is, it is energy shift, atomic energy shift by an external magnetic field. When we apply magnetic field, the energy level of hydrogen like this, it is basically it is degenerated, and the degenerated energy level shifted by applying magnetic field, and basically, and the energy level might be the UVB, like energy level like this. So we can deal with this G-man effect as a perturbation of hydrogen theory. So, and let's going on the energy, G-man energy of interaction between magnetic field and magnetic moment. And the energy is like this, mu dot B. B is the magnetic field, and the mu is the magnetic moment. And the minus means that this minus means it is any kind of potential. So then basically the energy minus energy means that it is stable when you apply magnetic field, and the magnetic alignment between the along the magnetic field direction is low energy. So, and when you apply magnetic field like this, and the magnetic moment also parallel, it is energetically favorable. That means that the minus sign. Here we should differentiate with the mu. It is a vector quantity. It is a vector. It means that the magnetic moment. And but in mu b, basically, and the unit of the magnetic moment, it is a Bohr magneton. A Bohr magneton is not a vector mu. It is a differentiate, and a Bohr magneton is a basic unit of magnetic moment. It is E h bar over 2 me. That is about roughly is about Planck constant times 1.4, and the unit is megahertz over Gauss. Basically, the magnetic moment of proton is approximately 1,000 times smaller than the electron, because, and we know, and the proton mass is about 1800 mass of electrons. So, and the proton magnetic moment, it is Bohr magneton is inversely proportional to the mass of electron. So in the proton case, and magnetic moment is very small, about 1800 times smaller than the electron magnetic moment. Here, then when you apply magnetic field, and let's consider for the normal G, there are two G-man effect. One is that normal G-man effect, and the anomalous G-man effect. Normal G-man effect is the G-man effect without spin. G-man effect without spin. We call it is a normal G-man effect. Here we ignore the electron spin and the fine structure. In the fine structure, we study for the fine structure consists with the first one in the relativistic effect plus spin-orbit coupling, spin-orbit interaction that result in fine structure of hydrogen. Also, we already know that electron spin, and here we ignore two terms for simplicity of calculation, but it is not realistic. So it is not realistic because real hydrogen have the fine structure also, and also electron spin should be taken into account, very important factor. However, and even it is not realistic case, but we should know that the basic notion, basic idea of the Zeeman effect. And here we apply magnetic field along the G direction, basically, and the G direction can be selected as a magnetic field direction. So in this case, that electromagnetic moment has originated by the orbital motion, not spin, because we ignore the spin. So the electronic magnetic moment and electronic magnetic moment only by orbital motion in this case. We ignore that because we ignore the electron spin. So orbital motion makes that electronic magnetic moment like this, minus E over 2me, and multiply the orbital angular moment, because this orbital in quantum mechanical point of view, and this magnetic moment of the orbital quantum number can make that minus mu b L over h bar. Here we should multiply the gyromagnetic ratio, and here it is here GL means that the orbital gyromagnetic ratio in most cases it is equal to 1. It is orbital gyromagnetic ratio. It is a factor for the orbital motion. Here, because it is magnetic moment, and also we should think about the energy term of the Zeeman effect is like E is that the minus mu dot B. So here the energy of this normal Zeeman effect is that minus mu L dot B, then it is a GL mu B 1 over h bar and L dot B. Here, because magnetic field direction is along the G direction, so then the L dot B it makes that along the G direction. So GL mu B and B over h bar, only the LG direction, because magnetic field direction is along the G direction. So we can deal with this perturbation energy. It is perturbation energy, and also we apply the we denote the G by the Zeeman effect. It is a Zeeman effect Hamiltonian, Zeeman effect perturbed Hamiltonian. So let's consider for the first order energy correction. First order energy correction is that the Zeeman energy in first order is the expectation of the Zeeman Hamiltonian, and we should think that the basis is the n orbital primary quantum number, and the L orbital quantum number, and L is that orbital magnetic quantum number. but here we do not consider for the spin in this case. So in S spin and spin magnetic quantum number, we ignore this. Quantum number. So we only consider for the n principal quantum number, orbital quantum number, and orbital magnetic quantum number, and also Hg prime is that Hamiltonian and the expectation NL and it should be diagonalized. It makes that matrix basically. So and this matrix should be diagonalized. So it is a basis is identical. It means that it is a diagonalized Hamiltonian. So because Hamiltonian of this Hg prime is written like this, and here. And basically here in this case LG is the operator, orbital operator, but the other term is the constant, and magnetic field is the static, not time dependent. Also it is a physical quantity. This physical quantity B is not deal with the operator, just only the quantum mechanical operator is that only LG. So here GL mu B and B over H bar is a constant, and NL ML and LG is operator, so it should be taken into account the expectation NL ML. We know, and this makes that here H bar ML. So it is because it is GL UB BML. Here it is a first order energy correction of the Zeeman effect without considering of the spin. So it means that here energy at for example in the 2p state, 2p state has 3 states. For example, 2p state, it is energy has 3 states. One is that ML equal to 1, because 2p is that L equal to 1, and there are 3 possibilities of ML is the 1, 0, minus 1. So 1, 0, minus 1 case, the energy splitting by applying the magnetic field, and external magnetic field makes that energy splitting like this. And here, so the energy of this m equal to 1 case and GL equal to 1. So it is a mu B and the 0 and the minus mu B energy. It is split like this. And it is, we call it is a normal Zeeman effect. And we already studied for the Stern-Gallac experiment in the first semester. And we already know that the Stern-Gallac experiment is that the magnetic field is not static, but it is n, whether for example it is S, and it is magnet like this, and this inhomogeneous magnetic field, and not a static, and it inhomogeneous. For example, inhomogeneous magnetic field and split the energy, and so here in the external magnetic field makes forced by magnetic field, inhomogeneous magnetic field can be write down as the negative gradient of G and the first order Zeeman energy. In this case, and we can make that another differentiation, and the partial Gman effect and the partial B, because Gman energy is a function of magnetic field, partial B and partial G. So in this case, this magnetic field gradient is not uniform, so it is non-zero. So here this magnetic field derivative of Eg, it makes that the GL mu B ML. So in most cases GL is 1, so minus mu B and the ML and the partial B partial G. And so this kind of magnetic field gradient can make the force, external force by acted in the electron.